All right, let me try another video solution from chapter 23. Now, this is that long, complicated chapter. But it also has to do with inductance. It says here in 64, it says the heating coils of a hair dryer are 0.8 centimeters in diameter and have a combination length of 1 meter and a total of 400 turns. What is the total self-inductance? Without going through all the steps again, we said the EMF is minus the number of turns times how the flux changes with time. And then, well, maybe I will go through all the steps. The flux from a solenoid being its magnetic field and its area, and then the magnetic field being mu naught times the number of turns per length times the current, sorry. Do a little blank there. But that's the magnetic field. So if you rearrange things, you would get like an n squared from that n, and then a mu naught. Then you would get area from here. I'll leave the derivative of the current here, and then over L. And so we defined the inductance and self-inductance to be this L. All the other factors, often made out of geometry, and then how the current is changing. So the fundamental physics is that it comes from the change in flux. But because that flux is coming from the current itself, we can change the derivative of the flux down to just the derivative of the current, and all these other factors like the area, the number of turns, and the length, and mu naught all contribute to the flux. So this is a long way of saying that the inductance of a solenoid then would be some geometric factors like how many turns, what's the cross-sectional area, and what's the length. And that's what I'm going to use here because they say it represents 400 turns. So I'll take 400 and square it. And mu naught, the permeability of free space, is 4 pi times 10 to the minus 7. And the area would be pi times r squared. And let me just come back to the question. It said that the diameter is 0.8 centimeters. So that means the radius is 0.4, and I'll just put centimeters and square it. So that's how you get the area, pi r squared. And they said it has an equivalent length then of 1 meter. And this should be measured in units of henries here. So let's see what we get here. Maybe I'll start with the 4 pi times 10 to the negative 7. And then multiply that by, I guess I'll do another pi. Then I will do that by the point, might see minus 2. So I'll go 0.004 squared. And then the other number I kind of skipped over here is the 400 squared. And then finally, well, divided by 1's not necessary, but what I come up with here is, it looks like a 1.01 times 10 to the minus 5 henries, although 10.1 times 10 to the minus 6 henries, which would be 10.1 microhenries for the induction. Okay. Then part B goes on to say how much energy is stored in them. And so the energy is this 1/2 Li squared that we derived with the inductor. And then we even used today in our chapter 34. But this would be then 1/2, and I can put in my induction now, 10.1 times 10 to the minus 6. And let's see what we got. Current is 6 amps, and so we'll square that. So that should be the area. Looks like I already got the inductance here in the calculator. So let me do times the 1/2, and then also times, and I'll just square the 6 in my head. That's 36. And hit enter, and we are looking at 1.82 times 10 to the minus 4 joules of energy. And then C, what is the average EMF? Well, let me come back and point out that this is the EMF, right? This is a special case of Faraday's law. The whole chapter is all about special cases of Faraday's law. So the general principle is Faraday's law, and then sometimes we do transformers, and sometimes we do, in this case, self-inductance. Anyways, so the EMF is minus L di dt. And if you don't pay attention to the negative, so you just kind of do the absolute value, and then you change it to an average, you can say the EMF absolute value on average is equal to how the current changes over a period of time. So it's not a derivative, but it's some kind of variation in the current over time. And the L we've already been doing. So the L is the 10.1 micro henries. And here they say, what is the average, so that's why I did the average, EMF produced in shutting it off. So the change in current would be 6 amps. And we shut it off in 5 milliseconds. And so taking the inductance up here, and then multiplying it by the 6 and dividing it by the 5 times 10 to the minus 3, I guess we would produce a small voltage, 1.121 volts. Although it's so small, maybe I'll write it as 12.1 millivolts. All right, and so there's 64.